Hey, week two. Excellent. Got through week one. And actually, let me just start by I likely thanked you once already for registering for this course, but I want to really thank you. I'm a bit of an educational technology geek, as you'll come to find out. And, it really is kind of cool for me to be part of this whole MOOC thing that we're all doing together. Just before taping this lecture, the number of students enrolled in this course reached 10,000. I know it's going to reach a lot higher, but that's kind of just a cool thing. It's a cool number. So literally, thank you. I really appreciate it, and on with the fun. So let me sit here, right? There we go. For this week, we are going to be talking about the brain, which lives somewhere around here. There's a lot to talk about in the brain, so I'm going to get right at it, okay? All right, so week two, lecture one, brain, the matter of mind. Let's start with some stats. Brain weighs about 3 pounds, which is about 2% of our total body weight. Now, in fact, if you compare us to other animals, that's actually a very high, what we call brain to body ratio. We have the biggest brain of any animal relative to the size of our body. Other animals like whales and such obviously have bigger brains, but they have bigger bodies as well. So at 2%, we have the largest brain to body ratio. But the really interesting thing is the brain's only 2% of the body, but look at the resources it consumes. 25% of our oxygen. So, 1 out of every 4 breaths you take goes to your brain, as a way of thinking about it. 70% of the body's glucose supply, the blood sugars, goes to the brain. So the brain is a very sugar-hungry organ in the body. And 25% of the nutrients you eat go towards keeping your brain healthy. So despite its relatively small size in the body, it clearly is a really powerful organ that's critical to our survival. There are about 100 billion neurons, but perhaps more important than the number of neurons are the number of connections between these neurons. 1 quadrillion. So million, billion, trillion, quadrillion. So there's a lot of connections, and that's really where the brain gets its computational power. The neurons itself are relatively simplistic, as you'll see, and actually transmit information in a relatively slow way. A common copper wire transmits information much more quickly than brain tissue does. But what the brain has is this tightly interconnected web of connections, and that's where the power really comes from. We'll get to that. But I want to, before I leave this slide, make this point that you may have heard people say things like, we only use 20% of our brain, or I don't know. I honestly have no idea where these numbers come from, and I can tell you that it's just complete not true. Complete not true. It just really isn't true. Every bit of tissue in the brain is used at least at some point to do something. It may be the case that at any given time, perhaps only 20% of neurons are active. So the brain at any given time may have 4/5 of its neurons silent, but any given neuron will come into play at some point in time, and probably not before too long. So I suspect, over probably even a relatively short period of time, an hour, you've probably used every neuron in your brain. So don't believe that when people say that only 20% of the brain is used and you just have to learn to untap the rest. We all use all of our brain. Okay, so onward. Let's get into the skull a little bit, literally. What this is imagine somebody was sitting there. This isn't a really nice thought to have, but we took a meat slicer or a guillotine and cut their head completely in half, including their brain completely in half, and now we're looking in. One of the things you see, first of all, when you look at a brain cut in half this way, is there seems to be a distinction between what people call white matter and what people call gray matter around the outside. So the white matter is a much denser tissue, and it literally does a couple of things. One is it provides structure, kind of like our dense bones in our body provide our body with structure that other stuff hangs on. It's kind of like the gray matter hangs on the white matter, and the white matter gives it structure, although clearly it's not nearly as dense as bone tissue would be. It also delivers nutrients and allows communication to go back and forth. So the white matter doesn't do a lot of the actual computation, not a lot of the figuring out of stuff. It does more of the communication of signals, more of the structure, and more of the delivery of nutrients. So, you know, it kind of underlies everything. But the real computational power seems to be all happen in these gray areas, what we sometimes call cortical tissue, the stuff on the outside of the brain. Now notice that these things are very kind of wrinkled. If we go back for a second, look at this brain. This is actually, this may confuse you a little bit, but the nice pinky stuff would actually be the gray matter. It doesn't look very gray in this beautiful, healthy pink brain picture. But what I want to stress for now is look at all the curves on this brain. We call the upper parts of these curves the gyruses or gyri. So, you know, anything that's on the top. Whereas these indentations we call the fissures. And in fact, although there's clearly individual differences, my brain would look a little differently than your brain if we plopped them out and sat them on the table. Generally, there's also a lot of similarities, and where these fissures lie tend to be in the same places, and they allow us to kind of segment the brain in certain ways. And we're going to spend a lot of time talking about 4 different parts of the brain when we get there. I won't do that now. But one question is, of course, why do we have these gyri and fissures? And I want to give you a sense. Let's sneak back to the other camera for a second. All right. So this is kind of what the brain, we think, happened with the brain. That as the brain was evolving, as we were evolving, brain power became very evolutionarily significant. Okay, the smarter critters were able to survive better and produce more offspring. And so there became this ever increasing need for more and more brain tissue. But of course the problem is our skulls are limited. There's only so much space in a skull. So how do you take something big and put it into a small area? Well, one of the things you can do is wrinkle it. Okay, and by wrinkling it, you can actually get it in a smaller area. And see, we have gyres and fissures forming there. And so this is the notion that if you actually took the brain and you unwrinkled it and flattened it all out, you would have a whole lot of gray matter. And the gray matter is where the action is happening. That's the powerful part of the brain tissue. So these wrinkles are all about getting as much gray matter as possible into a small skull. Kind of cool. All right. Let's now zoom in a little bit. Okay, this is gray matter, white matter. What is this stuff? So imagine we could zoom right in and look at the smallest sort of functional element within the brain matter. And what we'd see, and this is really just 2 depictions of the same thing, what we'd see is something that we call neurons. So this is like a nice artist rendition, very pretty. This is just more of a easy sketch to think about things with. But they're really representing the same thing, which is a neuron, what we call a neuron. Now these neurons have various parts to them. First of all, there's the body, just that central, what we call cell body. Here you see it here, in this one it's right here, and it has a nucleus in the middle. You see that in both as well. This is where the neuron will make decisions. It really makes the same decision over and over again. Well, what's that decision? It's deciding whether it's going to send a signal to the other neurons it's connected to. So you can almost think of this as like a Twitter kind of or social networking kind of thing. That every given moment you have to decide whether you're going to send out a tweet about something or not. But for you to send out something, there has to be enough reason to do that. Well, how do you know whether to do that or not? I'm mixing my metaphors here. I hope you stay with me. Here's how neurons work. They have these dendrites at the end, or in these nice artist renditions. This is where other neurons can communicate with this neuron. Okay, so what you see, for example, in the artist rendition here, this would be another neuron that it's sending signal. It's not actually connecting. If we could zoom in on what's going on here, you would see that there's a space between the sending neuron and the receiving neuron. So there's this little space that we're going to call a synaptic cleft. But this is literally how these neurons communicate. And so other neurons are communicating to this one, and they're telling it essentially one of 2 things. They're either saying, hey, get excited, get excited, get excited, or they're saying, chill, man, relax. So we call that an excitatory signal or an inhibitory signal. Okay, they're either trying to excite the neuron or they're trying to inhibit it. And now a bunch of different neurons are connected to this one. Some of them are trying to excite it, some of them are trying to inhibit it. And really what's going on in the cell body is it's summing all of these signals, and it's asking itself the question, not literally of course, mathematically and neurochemically, is there enough excitement for me to get excited? So it's literally comparing the how many excitatory signals am I getting, how many inhibitory signals am I getting. If there's enough of a difference, if there's enough more excitatory than inhibitory, enough to exceed some threshold level, then this neuron is said to fire. Okay, what's that mean? Well, what it means is this electrochemical process is initiated. These gates are open, which allow chemicals to flow back and forth. These chemicals have different charges, positive or negative, and so when they flow back and forth, they trigger this chain reaction, kind of like, in a sports stadium where people do the wave. One person does the wave, and then the person next to them, same idea. There's this chain reaction that happens down what we call the axon. So the axon is this very long tail, as it were, that leads from the cell body, and at the very end has these what we call axon terminals or terminal buttons. So if we go to the artist's rendition, you see here's the axon. And so the signal would translate down here, kind of like the wave in a sports thing, and then ultimately would come to one of these buttons, which is what we have the blow up here. And what then happens is this neuron releases some chemicals into the synaptic cleft, into that space between it and the receiving neuron. Those chemicals are received by these receptors. So they're special receptor sites that are channeled, they're shaped to receive certain neurotransmitters. And so if those neurotransmitters are released, this one catches them essentially, and that's how the signal gets from one neuron to the other neuron. And it could be an excitatory signal or an inhibitory signal. Just because this neuron's firing doesn't mean it's sending an excitatory signal. It could be trying to shut something down as well. But that's where the transmission actually happens. I'll have some videos at the end of this that I'll point you to that'll talk about that in a lot more specifics. But this is the general, lowest common denominator, smallest functional unit in the brain are these neurons. The neurons are important, but what's really important are all these connections. So if you kind of think about the way I've described this now, we have a given neuron getting input from a whole bunch of neurons, and then this looks like it's sending it to just one neuron, but that's not accurate. It would be sending its signal to a multitude of neurons. So it gets information from a multitude and it sends it to a multitude. So it's one part of a highly interconnected network. And that's really important to understanding brain processing, because if we look at something like pain, for example, pain reception, there's not a part of the brain, like a little tiny part of the brain that reacts to pain. Instead, the brain seems to respond to stimulation using what's called distributed processing. It represents the information in a multitude of areas simultaneously. Sometimes the specific information being encoded are sort of parts of the greater picture. So here's an example. This is brain areas that are related to pain processing, but we've kind of broken pain up into three aspects of it. The actual feeling that you're feeling, the emotion that feeling is causing, and any thoughts that might be triggered by this painful event. So just to give you a sense of that, imagine what you're feeling is muscle pain because you worked out last night. Well, there is a pain. There's a sensory feeling of that pain. There's an emotional feeling, which might be like a little bit of but when you combine it with the cognitive, you know that came from the fact that you worked out, and you probably feel good about working out. And so it could be that this affective, even though it's pain, it could be sort of a positive aspect that's linked to the cognitive fact that you worked out. So now if we look at the brain, we see that some parts of the brain are very reactive to the sensory aspects of it. Those are the green ones. Some parts are very sensitive to the emotional aspect, the affective aspect. You see those here, anterior cingulate especially. Other areas are reactive to the cognitive parts, much more frontal areas of the brain. And some areas are reactive to a combination. So this sort of brownish color reflects the combination of sensory and affective. Those are areas like here. And finally, the purplish represents the combination of affective and cognitive, as you're seeing here, here, and here. Now, I'm not going to get into what all these brain areas are right now. The point I want you to take from this is that that experience of pain is a distributed experience. It's represented by multiple parts of the brain simultaneously, thanks to these highly interconnected networks of neurons. That's a really important point because the brain has to deal often with noisy inputs. So let me make this clear. Here's an apple. This is a distributed representation, the way I present it to you. When we see visual things, they are distributed representations. What I mean by that is, if we imagine the screen and the pixels lit here, what we really have is a combination. Some pixels are sending out a white signal. Some pixels are sending out a red signal. Some are sending out a white signal in the middle of a bunch of others that are sending out a red signal. The brain is taking all of this information and somehow combining it in order to form this concept that we all have of an apple. So we can see an apple from all this information. Now imagine, instead of thinking of the pixels, imagine these were neurons reacting to something out there. And again, all these neurons can be sending their signals, and that pattern of activation across the neurons could be what actually defines the fact that this is an apple we're experiencing. Now, the nice thing about this is that it's very tolerant of noise. Okay, let me throw this image up here. Let's say we put a bunch of dots over here to block out what the information that some of the pixels are sending, if you want to think of it that way, or imagine some neurons stopped sending signals. Well, just because a bunch of neurons are not operating well or not giving us a clear signal, we can still see the apple. If there are enough that are sending consistent activation patterns, then we can still interpret what's out there, even though there's a whole lot of noise. So when we talk about graceful degradation, what we mean is if parts of brain tissue actually died, you still have an ability to interact perfectly well. No single neuron is going to suddenly make you not see what apples are anymore. And this also allows the brain to be very tolerant of noise, and that's really important. So let me give you an example of that for a second. You've been listening to my voice, but I'm going to shut up for a second. It'll be a rare event in these lectures, I promise you. But I'm going to shut up for a second, and I want you to listen to other sounds that are around in your environment. Okay, here goes. Okay, so hopefully you heard, I don't know, maybe traffic sounds, maybe voices, maybe the heater in your home, maybe, hums of fans, who knows. My point is, as I'm speaking, there's all of this other noise around, and your brain has to be able to deal with that. And it's by using these distributed representations that it's able to do that. And that's critical because when we talk about brain functioning in general, you'll see that there's always noise present. And that's part of the brain's power is its ability to function in noisy environments, to function really effectively. Okay, so that was a big intro of the brain, and we're going to start going into other more specific issues. But here's a couple videos. They're related to recreational drugs. A lot of people find recreational drugs interesting for whatever reason, but they also give you a really good sense of how that synaptic transmission works, information flowing across the synaptic cleft, and the critical role that neurotransmitters play, and how these drugs are having their effects by mimicking or blocking or interfering in some way with the natural way the brain works. So you'll learn a little bit maybe about cocaine and marijuana here, but you'll also learn a whole lot about synaptic transmission, and that's why I have those here. I have a Wikipedia reading, but I also have a neat website where you can interactively kind of learn about the brain. So another great way to follow up from this. Alrighty, so we will continue on. Our next lecture is going to talk about the whole issue of why we can suddenly get so excited when something, say, scary happens, and the idea that there actually is kind of a switch inside of you that can switch you from being relaxed to ready, and how the brain relates to all that. All right, see you in the next one. Have a great day. Bye bye.